Okay, so this is the key to worksheet 2.6, part 1. And on this worksheet, you want to find the domain of each of the following functions. Now, some functions are polynomial functions, and some of the functions are rational. So this worksheet deals with polynomial and rational functions. Okay, so polynomial and rational functions. Okay, now you want to state the domain in interval notation. Now, on my math lab, they may ask you to state it as an inequality, so I'll mention that as well. But if we go to, let's say, number 3, all right, so number 3, you have to recognize that that's a rational function. So number 3 is a rational function. And you have to remember that, that to find the domain of a rational function, so the domain of a rational function, okay, would be any value for x, so remember the domain is set of x coordinates. So any value of x for which the function is not undefined. Okay, so any value for x for which the function is not undefined. So remember that and we're doing number 3 right now, so that in a rational function, a function is undefined. A rational function is undefined when the denominator is 0. So let me write it this way. A function is undefined for values of x for which the denominator is 0. For which the denominator is 0. Okay? All right, so that was a quick review from the lessons dealing with this. So number 3, if we go back to number 3, we have the function h of x is equal to 5 divided by x minus 7. All right, now, so if we look at this rational function, we want to find the domain of this rational function. So what are the values of x that I can use in this domain and get a y value back? All right, so that's going to be important when you start graphing these. And so in a rational function is undefined when the denominator is 0. So the question is, what value of x makes that denominator 0? So if you're going to find where the rational function is undefined, where the denominator is 0, all you do, first of all, is set the denominator equals 0. It does not matter what the numerator is. In this case, it's always 5. It's going to be 5 always for this rational function, but that doesn't matter. It's what occurs in the denominator. The denominator cannot be 0. All right, so remember, you cannot divide by 0. And so if I want to find out where this is 0, and you could have looked at this and determined that when x is 7, this is 0, right? But there are situations where you can't really just look at it. So what you want to do is take this denominator and set it equal to 0 and solve for the variable. Since this is a linear equation, I solve for x, I get x to be 7. So what I found here was the value of x, this is a value of x, this is a value of x, the value of x where h of x is undefined. Okay? All right, so where h of x is undefined. And so now what you do is realize, hey, so I can use any other number for x except 7. And so since I want to write this in interval notation, then the way to do this is this. So you put 7 on the number line. And so notice that this number 7 I can't use. I'm going to cross it out. And so I can use any other number that's on that number line, any real number that's on that number line. 7.000043, 7.188892674, and so on. Negative 8.25. Okay, so any value for any real number except 7. And so what you do here to find the interval notation, so your answer will be from negative infinity to 7. Since I can't use 7, since 7 is not in the domain, you're going to use parentheses. So negative infinity to 7, parentheses, union 7 to infinity. So that's interval notation. So that means all real numbers except 7. So you have parentheses there. As an inequality, or as a set notation, you would say something like this. So the answer would be, on my math lab, you would say the set of x's such that x does not equal 7. So that's how you would say that on my math lab. So this is my math lab, and this would be interval notation. Okay. So this, remember, means a set of x's such that x does not equal 7. So any real number except 7. So any real number except 7. Okay? All right, now, so that was number 3. So number 3, I'm going to go ahead and put this right here. Since I wanted interval notation, I'm going to go ahead and state it as such. So that's going to be negative infinity to 7, union 7 to infinity. All right? Now, so we talked about a rational function. Now let's look at polynomial functions. All right, polynomial functions. So remember, a polynomial function has this form. So a polynomial function has this form. So it has a form f of x equal some number x to the n power. All right, where n is greater than or equal to 0. Okay, and n is a whole number. Let me rephrase it this way, where n is a whole number. And so remember, your whole numbers are 0, 1, 2, and so on. Okay? All right, no decimals. All right, no decimals. No fractions, just whole numbers, 0, 1, 2, and so on. Okay? So it has that form. All right, so your exponent has to be a whole number, and your coefficient can be any real number. All right, so it has to have that form. So you could have plus a1 x to the n minus 1. Now be careful. So as long as, maybe I should, since I have n here, maybe I should say where exponent is a whole number. All right, so your exponent has to be a whole number. All right, so the exponent is a whole number. All right, so for example, number 2. So see that in number 2, we have g of x equal 2x squared minus 5x minus 2. So notice this exponent's a whole number, this exponent's a whole number, then you have your constant, right? And keep in mind that you may say, well, where does 0 come in? Well, from here, watch. So g of x equal, this is the same thing as saying 2x squared minus 5x minus 2x to the 0 power. All right, so remember, a constant, your variable is always going to be raised to the 0 power, because x to the 0 power is 1. 1 times negative 2 is negative 2. All right, so that's where that 0 comes from. So where the exponent is 0, 1, so that's the 1. So that's where your constant becomes. Okay? All right, so notice this. So all of the exponents are whole numbers. All right? And so this is a polynomial function. In fact, when you graph this, if you recall, and I'm just going to do like this, when you graph this, remember the domain is all real numbers. So if you go back to that section where we started talking about graphing quadratic functions, your domain's all real numbers. And so we learned in a future lesson at that point that the domain of all polynomial functions, is all real numbers. The domain of all polynomial functions is all real numbers. Okay? And so so since this is a quadratic function, it's a polynomial function, I'm just going to say the domain in interval notation is negative infinity to infinity. All right, now on MyMathLab, it's just going to say this. On MyMathLab, it's going to say all real numbers. And that's what you write, all real numbers. Okay? So that's what MyMathLab is going to say. All right, now, in some textbooks, it'll say something like this: the set of x's such that x is any real number. All right, so these two mean the same thing. So in MyMathLab, you just say if the domain's all real numbers, you'll say all real numbers. But some textbooks, they'll have this as the domain. So the set of x's such that x is any real number. All right. Now on the worksheet, you're going to write this. So that's interval notation on the worksheet. Okay. All right. So that's going to be negative infinity to infinity. And then again, notice this is a line. So that's a polynomial function as well. All right. And so the domain is going to be all real numbers. So over here, notice that's a polynomial function as well. So the domain is going to be all real numbers. All right, now number 5, all the rest here are rational functions. And so to find the domain of a rational function, you have to determine what value of x makes my denominator 0. So what I would do is I would take that denominator, and find out where it's equal to 0. And so notice this is a linear equation. So when I solve for x, I get x to be 5/2. Okay? And then what I would do at that point is, let me go ahead and use another sheet of paper. Okay, so then what I would do at that point is I would put 5/2 on the number line, because remember what that means in number 5. What that means is that the domain will be any real number except 5/2. So I'll cross it out. And so notice that this x divided the number line into two intervals. So I'm going to say negative infinity to 5/2 union 5/2 to infinity. And so that'll be your answer. So negative infinity to 5/2 union 5/2 to infinity. Okay? Now, on MyMathLab, you would probably be, your answer would look like this. The set of x's such that x does not equal 5/2. Okay? All right. Number 6. So notice number 6, you have again a rational function, except this time, if you look at your denominator, it's already in factored form. And so that's easy to deal with. So number 6, your function is f of x equal 7 divided by x plus 2 times x minus 5. And so basically here, you just have to set the denominator equal to 0. So x plus 2 times x minus 5 equals 0. And so remember, you're going to use a zero factor property. So you're going to set each of these factors equal to 0. So x plus 2 equals 0, x minus 5 equals 0. And so you have these two linear equations, so x equal negative 2, x equal 5. Okay? All right, so what you found is that your domain would be any real number except those two. So negative 2 makes the denominator 0. You can see that. Negative 2 plus 2 is 0. 0 times negative 2 minus 5 is negative 7. So 0 times negative 7 is 0, right? Okay. So, but you got to find the interval, right? You got to find the interval notation. So what you do at that point is you put those two in the number line in order. So negative 2, 5. So you can't use those, so you cross them out. And so notice that my domain would be any real number except those two. So those two values that make my denominator 0 divides the number line into 3 intervals. So I go from negative infinity to negative 2, union, and then negative 2 to 5, and then union 5 to infinity. Okay, and so that will be your answer in interval notation. So that would be number 6 here. So you would say negative infinity to negative 2, union negative 2 to 5, union 5 to infinity. All right, now on MyMathLab, you would probably write it like this: the set of x's such that x does not equal, and it'll probably, since there are two of them, they'll probably tell you to separate them using commas. So you say -2, comma 5, and that's it. Okay? All right, number 7. Number 7, if you look at your rational function, here's my denominator. So I got to figure out where's his denominator equal to 0. And there are a couple of ways you could do this. You could use the square root property. Since there's no x term, there's an x squared but no x term, you could bring the 16 over. So I get x squared equals 16. And then using the square root, taking the square root of both sides, don't forget plus or minus, I get x equal plus or minus 4, right? Or you could have factored. You could have said x minus 4, since that's the difference of two squares, times x plus 4 equals 0. And then just like we did this one, you have a product that's zeros, that's equal to 0. So you're going to set each factor equal to 0. So x minus 4 equals 0, x plus 4 equals 0. So x equals 4, x equals -4. All right, same thing here. So it didn't matter which approach you used. But notice that for this rational function, number 7, my domain would be any real number except positive and -4. So I'm going to put that in the number line in order, -4, 4. I'm going to cross those out because I can't use those. Those make my denominator 0. And notice I have 3 intervals. And so I'm going to say -infinity to -4, union -4 to 4, union 4 to infinity. And in my math lab, you're probably going to say the set of x's such that x does not equal -4, comma 4. They're going to ask you to separate them using commas. So that's what you do. Okay? All right. So that was number 7. So you're going to say -infinity to -4, union -4 to 4, union 4 to infinity. Okay, now number 8. So some students get confused with number 8 because they forget about a couple of things that they've learned in the past. So there's a difference between 7 and 8. 7, if you look at that, the denominator, this right here, that's the difference of two squares. So I can factor this and get some real numbers. So those two real numbers make that denominator equal to 0. 4 squared is 16, 16 minus 16, 0. But if you look at number 8, if I look at x squared plus 16, and I want to find out where does that equal to 0, I mean, if you think about it, some of you want to say 4. Well, that's not true because 4 squared is 16. 16 plus 16 is not 0. That's 32. Same thing for -4. -4 times itself is 16. 16 plus 16 is 32, not 0. Remember, that's the sum of two squares. And so remember, the sum of two squares cannot be factored. And so basically what this means here is that this is never 0. So if I go back to my function, h of x equal -3 divided by x squared plus 16, this rational function is never undefined. All right, so that's never undefined. So what that means is that the domain is all real numbers. Domain is all real numbers. Okay? And so you're going to say number 8, you're going to say -infinity to infinity. All right, number 9. Now what you're going to have to do number 9 is, again, this is a rational function. You got to figure out where is the denominator equal to 0. What makes my denominator 0? So you got to take this trinomial and factor it. So you got to figure out 2x squared minus 7x minus 15. You got to figure out where's that 0. And so if I factor, I get 2x, x, and you could use a quadratic formula, but it's factorable. Let's see, 5 and 3, so negative plus. All right, so you factor like this, and then you set each factor equal to 0 because you have a product at 0, so you have to use a 0 factor property. So I get 2x plus 3 equals 0, x minus 5 equals 0. And so when I solve each linear equation, I get x to be -3/2 and x to be 5. And so what I found was that my domain would be any real number except those two. And so if I put that on a number line in order, negative 3 halves, 5, and I cross those out, then my domain would be those three intervals, not including these two numbers. So my domain would be negative infinity to negative 3 halves, union negative 3 halves to 5, union 5 to infinity. Now in my math lab, you would say a set of x's such that x does not equal those two values, negative 3 halves, comma, 5. All right, so that will be number 9. So negative infinity to negative 3 halves, union negative 3 halves to 5, union 5 to infinity. All right, and then number 10, so you have this rational function. My denominator is 3x. And so you got to figure out what value of x makes this this term equal to 0. So if you think about it, 3 times 0 is 0, right? Or some of you may need to go ahead and divide by 3, and so you get x to be 0. And so that's the only value of x that I can't use in my domain because it makes my denominator 0. And so you put that in the number line, cross it out, and so you get negative infinity to 0, union 0 to infinity. So negative infinity to 0, union 0 to infinity. All right? So that's the key to section 2.6, part 1. Oh, and don't forget, in my math lab, you would say, in my math lab for this one, you would say the set of x's such that x does not equal 0. All right? Okay, so that is the key to section 2.6, part 1.